Thank you for joining us today. My name is Michael St. Laurent. I'm a meteorologist with the Hydrometeorological Design Studies Center in the Office of Water Prediction in the National Weather Service. Today I'm going to be talking to you about NOAA Atlas 14 Precipitation Frequency Atlas of the United States. So what is NOAA Atlas 14? The calculation of precipitation frequency estimates has historically been the responsibility of NOAA. Over time, estimates were published in different technical papers, documents, and atlases such as TP40, TP49, Hydro 35, and NOAA Atlas 2. Since the early 2000s, HDSC has been updating these long outdated precipitation frequency estimates, developed in the 1950s to the 1970s, and publishing them in NOAA Atlas 14. Under the current funding model, Atlas 14 work is supported from external sources via cost reimbursements made possible by memoranda of understanding between NOAA and a changing set of partner and customer agencies. This approach generally dictates that updates are done in volumes based on state boundaries, which are produced in a serial, non-parallel workflow stretching over many years. Typically, several states are updated as a group to reduce costs, and their estimates are published as a volume. States and territories associated with each of the volumes are illustrated in the figure. Volume 11 for Texas is the most recent Atlas 14 volume published in 2018. Funding is currently not available to update the estimates for the 5 remaining northwestern states with no NOAA Atlas 14 coverage. So what are precipitation frequency estimates? A precipitation frequency estimate for a given location is defined as the depth of precipitation for a specific duration that has a certain frequency of occurring. When precipitation depths or intensities are offered for a range of durations and frequencies, the resulting set of curves are referred to as depth duration frequency curves, also known as DDF curves, or intensity duration frequency curves, also known as IDF curves. Atlas 14 DDF curves cover durations from 5 minutes to 60 days and frequencies up to 1,000-year average recurrence interval. Frequency can be described in terms of an annual exceedance probability or average recurrence interval. The annual exceedance probability, or AEP, is a probability associated with exceeding a given amount of precipitation for a specified duration at least once in any year. For example, an AEP of 1 in 100 equates to a 1% chance of the amount being exceeded at least once in any year. Average recurrence interval, or ARI, is the average time between exceedances of a given precipitation amount for a specified duration. An alternative term is return period, which was referenced in many engineering design manuals to describe acceptable risk of failure. For example, 100-year amount on average occurs every 100 years. Where are Atlas 14 estimates used? The National Weather Service uses Atlas 14 estimates in conjunction with their near real-time and forecasted multi-sensor precipitation data to monitor current and forecasted storm events and provide situational awareness of extreme storms capable of producing flash flooding. They are also used by media and others to convey the rarity of an extreme storm. For example, you may hear the term 100-year storm. HDSC also analyzes frequency of selected significant storm events. More information on the analysis is provided on the webpage that can be reached using the link shown in the left figure. Atlas 14 precipitation frequency estimates serve as the de facto standards for designing, building, and operating infrastructure to withstand the forces of heavy precipitation and floods, or to plan the availability of water supplies. They are referenced or used in calculations in local, state, and federal codes, regulations, and permits. For example, they appear in voluntary consensus standards for designing and operating projects such as municipal stormwater management systems, sediment control measures on construction sites, culverts, roadways, bridges, wastewater treatment plants, and many more. Selection of design criteria for particular infrastructure are governed by cities, local, or state governments, and depend on an acceptable risk of failure. As shown in the example on the slide, a highway culvert in a low-traffic area may be designed on a 5 to 10-year average recurrence interval, while levees around cities are designed on 50 to 200-year average recurrence interval. They are also used in the delineation of floodplains and in the regulation of development in floodplains for FEMA's National Flood Insurance Program. Why is it important for regulatory authorities to reference the most recent NOAA Atlas 14 estimates? When precipitation frequency values used in a design are overestimated, it can cause unnecessary costs to taxpayers or developers. However, if an estimate is too low, it can cause unintended destruction of property and loss of human life. Atlas 14 estimates supersede estimates from the 1950s to the 1970s, published in various NOAA documents. They are superior to the previous NOAA estimates in terms of accuracy, reliability, and resolution. Atlas 14 estimates are based on more data in terms of the number of stations and record lengths, and they include data from the most recent years when several significant events occurred. Statistical methods used are more robust than those in previous studies. Estimates are available at high spatial resolution, in contrast to TP40, where manual interpolation from cartographic maps is needed. Finally, estimates are now provided for a wider range of frequencies, durations, and uncertainty measures. Even so, many design manuals still reference superseded NOAA estimates. An example shown in this slide clearly demonstrates why it is important to update design manuals. The City of Austin has updated its floodplain regulations based on Atlas 14. The most significant change to the floodplain regulations is that the current 500-year floodplain is now used as the regulatory 100-year floodplain until new floodplain studies are completed. Where can you find NOAA Atlas 14 estimates? They can be downloaded from the Precipitation Frequency Data Server website. The PFDS homepage, shown in the figure, has a clickable map of the United States and affiliated territories, and a side menu on the left with various links. When Atlas 14 products are needed for a specific location only, clicking on an appropriate state on the map or selecting the state name from the drop-down menu will cause an interactive map of that state and its surrounding area to be displayed, from which relevant information for a selected location can be obtained. The submenu under the Precipitation Frequency tag is used to download various Atlas 14 products applicable across the states in each volume. Detailed information on the underlying data and functioning of the PFDS is provided on the home page. After the location is selected, all precipitation frequency and confidence limits estimates are displayed directly below the map in three separate tabs: PF Tabular, which is displayed by default, PF Graphical, and Supplementary Information. The PF Tabular tab provides DDF or IDF data in tabular format together with the 5th and 95th percentile confidence limits. For example, in the center figure, the 24-hour 100-year estimate of 5.26 inches is highlighted in red. The PF Graphical tab shows data tables as depth, duration, frequency curves, with an option of also displaying curves for the upper and lower bounds of confidence intervals. Lastly, the Supplementary Information tab provides links to additional data and information applicable for that location, such as documentation, precipitation frequency and confidence limits grids in GIS-compatible formats, cartographic maps, temporal distributions, seasonality graphs, time series data, and various miscellaneous information. Atlas 14 products applicable for the whole area within each volume can be accessed through the links on the left menu bar on the PFDS homepage below the Precipitation Frequency tab. This includes GIS grids, cartographic maps, time series data, temporal distributions, and the documentation. How are the estimates calculated? The process starts with data collection. For example, in the Northeast, we collected data for approximately 7,600 stations from 22 federal, state, and local agencies. We then move on to station screening. This includes examination of station locations, screening for duplicate records, removing unreliable records, and so on. The analysis approach is based on annual maximum series, or AMS. AMS for each station is obtained by extracting the highest precipitation amount for a particular duration in each successive year. All AMS are quality controlled. DDF curves at individual stations are computed using regional frequency analysis on the AMS across all durations and then interpolated to a 30 arcsecond grid. All Atlas 14 volumes are subject to external peer review which provides critical feedback. Estimates are re-examined based on the input received during the review process and revised as necessary. Finally, before all products are published online, various supplementary information is developed. The Atlas 14 process, or any other frequency analysis process, carries a lot of uncertainties. Data errors, station record length, and spatial coverage are a few examples of this uncertainty. In the top left figure, changing the record length can cause an at-station 100-year estimate to vary between 6.6 and 17 inches. The bottom left figure shows 1-hour AMS for Ithaca, New York. Data digitized from paper forms in the pre-1948 period, shown in red, increased the at-station 100-year 1-hour estimate from 1.6 to 2.6 inches. The top right figure shows an example of a data error where 9 inches of snowfall was archived as 9 inches of liquid precipitation, which has been corrected in our AMS. Finally, the figure in the bottom right demonstrates differences in station density for daily durations between two volumes. Clearly, the more dense network of stations improves estimates for ungauged locations. Frequency analysis methods themselves can have a large impact on the estimates. This can range from distribution selection, choice of parameterization method, stationary versus non-stationary approach, regionalization method, optimization of DDF curves to maintain consistency, and finally, interpolation. For example, as shown in the top left figure, depending on what type of distribution is selected among 7 that passed all statistical tests, 100-year estimates vary between 11 and 13 inches. For rarer frequencies, differences are even more prominent. 1,000-year estimates vary from 13 to 22 inches. Choice of interpolation method affects estimates at ungauged locations. For example, some methods, such as Atlas 14, incorporate terrain, while others, like TP40, do not. What are the areas that need improvement? The first one is methodology. The current Atlas 14 approach was developed in the 1990s with improvements in later volumes. One of its assumptions is that the extreme precipitation characteristics are stationary. That assumption is questionable in the presence of non-stationary climate. Together with a team of scientists from Penn State University, the University of Illinois at Urbana-Champaign, and the University of Wisconsin-Madison, HDSC has worked on assessing the suitability of different non-stationary frequency analysis methods with respect to the Atlas 14 process. We performed analysis on daily and hourly precipitation data from Atlas 14 Volume 10, Northeastern states. We also evaluated CMIP-5 downscaled datasets based on their ability to reproduce observed precipitation frequencies from Volume 10. Research indicated that the downscaled datasets can replicate many features of the observed precipitation frequencies. Rather than including the time as a covariate in the model directly, climate model outputs are used to incorporate the relationships between precipitation and other climate factors, as well as make projections based on different emission scenarios. Those findings were used to develop a non-stationary approach that will be able to efficiently translate future climate scenarios into a product that will be used in the next Atlas 14 update. This will be presented at a later date at a webinar. We also proposed 3 major additions to the current suite of Atlas 14 products. First, the most significant one is the addition of aerial reduction factors, or ARFs. Atlas 14 provides point estimates, which represent limited area around a given point. For applications requiring watershed estimates, point estimates must be converted by using ARFs. Despite many proposed methods for calculating ARFs, most engineers continue using curves produced by the Weather Bureau in 1958. These are assumed to be the same for any location and return period in the United States. HDSC made some strides in determining ARF methods suitable for coupling with Atlas 14. However, due to lack of funding, this work has not progressed. Our goal is to derive regional ARFs and develop a web tool to delineate watersheds and calculate watershed-based precipitation frequency estimates. Second, another enhancement is the development of a reliable design storm product that can be used in engineering design, together with guidance on how to use the product. While Atlas 14 provides precipitation frequency estimates for a given duration, designers are often interested in how the precipitation falls over time, and not just the total amount. Therefore, they must find a way to distribute the Atlas 14 estimates over time. Lastly, the current Atlas 14 method provides only bounds of 90% confidence interval. Several state and federal agencies indicated that other widths are of interest for their applications. Development of confidence intervals of vary width would be another enhancement. None of this proposed development will happen without proper support. Funding for Atlas 14 work comes from external sources. This current approach dictates that updates are done as separate volumes based on state boundaries. Each volume is completed independently from the other and is often separated by multiple years. This approach results in discontinuities in the estimates at boundaries of adjacent volumes, which in turn creates an issue for the users as they typically consider the watersheds, not state-based boundaries. Atlas 14 estimates should be updated on a regular cycle of approximately every 10 years to improve the overall product through the inclusion of more data in terms of the number of stations and the record lengths, and lastly, the use of modern methods capable of accounting for non-stationary climate. 19 states covered in volumes 1 and 2 were last updated in 2000, and NOAA-based estimates for the 5 northwestern states are more than 50 years old. Having a continuous and sustainable funding approach will be a small investment that would result in significant returns and benefits for infrastructure design in the United States. So thank you for joining us today. Here's a link to our website and our email, and if you have any questions or comments, we'd be happy to hear from you.